Hello, and welcome back to Communicable, the podcast brought to you by CMI Communications, ESCMID's open access journal covering infectious diseases and clinical microbiology. My name is Angela Huttner. I'm an infectious disease doctor at the Geneva University Hospital in Switzerland and editor-in-chief of CMI Comms. I'm joined by my co-host, Josh Nosanchuk, fellow editor at CMI Comms. Note, Josh is our official fungal editor, but the truth is, he is like a Swiss Army knife. He handles papers that may have nothing to do with fungi. This is because he's an all-round infectious disease clinician and professor of ID and medical microbiology at the Albert Einstein College of Medicine in New York, where until recently he was also Dean of Education. Josh, we're so glad you're here.
Oh, thank you, Angela. And we're extremely excited today to host our friend, Dr. Arturo Casadevall, a physician scientist and microbiologist who serves as the Bloomberg Distinguished Professor of Molecular Microbiology and Immunology and Infectious Diseases at Johns Hopkins University. He's internationally recognized for his research on fungal pathogenesis, microbial evolution, and host immunity, particularly in the context of Cryptococcus neoformans and emerging fungal threats. Dr. Casadevall has been a leading voice in exploring the links between climate change and the rise of fungal pathogens, including proposing the thermal barrier hypothesis and contributing to the hypothesis that Candidozyma auris emerged due to global warming. Among numerous other remarkable activities, Dr. Casadevall is also exploring how outer space affects fungi and their microbial products. He has been honored with the election to several prestigious academies, including the National Academy of Sciences and the American Academy of Arts and Sciences. He's the editor-in-chief of MBio for the next 6 days, after which he will step down after 15 years of leading the journal as the inaugural editor. On a personal note, Arturo was my postdoctoral advisor. Nearly 30 years on, we're still actively collaborating on studies of fungal melanin. Arturo, welcome to Communicable.
Thank you, Josh, for a very nice introduction, and thank you, Angela. I'd love to be here.
Before we get into climate change and fungal spread, we do want to announce that Arturo is the founder of Melatech, which is a company that makes melanin for a variety of applications. Josh and Arturo, they have been funded together by National Institutes of Health since as early as 1998 to study the basic biology of melanin in fungi.
Thank you, Angela.
So moving on, as our listeners know, we always start our episodes with a get to know you question. Here's the question, a bit quirky this time, but here it is. What is a sound, yes, a sound that makes you happy when you hear it? Josh, you first.
So I love the sound of a bugle call. And why? Because in my phone, that's what I set for my wife and my 2 children. And so when I get a text message from them, it makes a completely different sound than anybody else. And I know they're reaching out, hopefully for something good, but it makes me smile whenever I hear it because I know it's my family. How about you, Angela?
Oh, that is so sweet. My favorite sound, I think, is a little more mercenary than that because my favorite sound is the coffee grinder getting ready to make my coffee in the morning. And I think it sounds better when my husband's making it and not me. It sounds really good. There are certain occasions in the year where he brings me my coffee, not very frequently, but he does sometimes bring me my coffee, birthdays, Mother's Day, etc. And it's the best sound in the world. Last but not least, Arturo.
Well, that's a hard question. I didn't expect such difficulty early on. I think that given that I had a lot of problems with my heater during the past winter, the sound of the heater coming on makes me happy because I know that at least we're going to be warm for the next hour or so.
But right now, Arturo, it's 100 degrees in here.
Right. Well, I know. But we were trying to think of noises, and I just think of the boiler going on, that special noise that goes to the house.
So to the topic, Arturo, I just want to set the scene here. You said in your recent ESCMID Excellence Award lecture back in Vienna that passed its prologue. Can you tell us about the Permian age and how it ended? And how does that compare to what's happening now?
So the end of the Permian, which is known as the Permian extinction, is the worst cataclysm that happened to life on Earth. 95% of the biosphere died. Organisms that have been around since the Cambrian essentially disappeared for example, tribolites. It's always been a mystery as to what happened. But what is evolving as the best hypothesis at the moment, and remember, these things can change with time, is that there was a giant fire that went through a coal vein. There was coal at the time, and set up a fire that may have lasted as long as 80,000 years. And this fire is where is now Siberia, dumped into the atmosphere enormous amounts of carbon dioxide. And this set off a cataclysm that involved global warming, acid rain, acidification of the oceans. And even though it happened over 80,000 years, the biosphere could not adapt. And what we need to keep in mind is that we are doing the same thing by burning fossil fuels, but we are doing it in a couple of centuries.
Yeah, and we've gone in the past 100 years from 2 billion individuals to over 8 billion individuals. It's been an incredible change. And you've written about how the global temperatures are doing many things, but also that they're selecting for thermotolerance in fungi. And I'm wondering if you could share thoughts on specific types of fungi that you're worried about, and how close are they to breaching the mammalian thermal barrier?
So you're absolutely right, Josh. When you're talking about temperature, you got to keep in mind that if you change 1 degree, you change everything in a cell, because it affects everything from membrane fluidity to how rapid enzymes work, to metabolism, to all that. The fungal world is a cold-loving world. They are colder than the environment. And most of the fungi do very well in temperatures that are at the ambient temperatures. So we are protected. I mean, most humans that are not immunosuppressed don't have to worry about invasive fungal diseases. I mean, that is remarkable, because insects, salamanders, snakes, frogs are being decimated by it. And this enormous protection is coming from 2 pillars. We have adaptive immunity and innate immunity, and the other one is we are warmer than the environment, so we can keep stuff out. Think about the frogs. The frogs have great adaptive immunity, innate immunity, but they are room temperature, and they're being decimated by a Chytrid fungus. So the concern is simple, that if most of the fungi in the earth today prefer ambient temperatures, as the ambient world gets warmer, they adapt or die. And most things can adapt. So some of these organisms that have pathogenic potential, that are currently not recognized as fungal pathogens, may begin to turn up in our patients. We think, at least we have proposed, that Candida auris was the first example of this threat.
So following on that, Arturo, I wanted to ask you indeed, what is the ecological or climatic evidence supporting this hypothesis that climate change is one very possible driver behind the emergence of Candida auris? What makes you think it's that, as opposed to other origins, simply like selection pressure from antimicrobial use, etc.?
So there are 3 possible explanations out there for the emergence of C. auris. One of them was that it was there all along, and we didn't know it. So that is being largely eliminated by people going back into collections. And it's just not there. I mean, you may find an isolate here and there, but this is something that is new to medicine. The second idea is that somehow the use of azoles in agriculture resulted in this organism emerging. I can understand how drug resistance will emerge from the use that is being documented, for example, in Aspergillus, that if you use it to protect the crops, you're also selecting for everything else that is on the soil. The problem that I have with that is that I don't see a very clear connection between drug resistance and increase in virulence for this to emerge all of a sudden. Because you should imagine that it was there previously and it wasn't drug resistance and then it came back. To me, the greatest mystery that needs to be explained is how this organism emerges simultaneously in 3 continents, and the isolates are not related. The 3 continents are South America, Africa, and the Indian subcontinent. And it's not like somebody took a plane and brought it. These things are so different that some people are talking about even making subspecies. Since then, there have been 3 other emergences that we know of, one in the Russian Federation, one in Iran and the other one in Singapore most recently. And again, they're not related. So I ask you and I ask the listeners, what is a common denominator for all these regions that is leading to these emergences? And the only thing I can think of, different climates, different societies, different levels of resource use, is that they're all getting warmer.
So I think that's incredibly insightful, but expanding on that, how is our changing world accelerating dispersion of fungi? We have forest fires, we've got changes in water movement in the Gulf Stream, for example, and other natural shifts. How does that tie into Candida auris as well as other threats that we should be aware of?
I think that currently we don't have evidence that movements are contributing to this. These appear to be localized. Of course, if you take a patient from one of these places and move it to another place, you're going to transfer the organism with it. But I think, Josh, you're getting at a deeper issue here. And the deeper issue is that fungi are at least 6 million species of this, and that they are being moved around and they've been put under tremendous selection pressure by the climatic change and things that we're doing. So I think that we should expect the unexpected.
So one thing you've talked about in the past, Arturo, was the Vancouver Island and the Cryptococcus gaddii and how that may have gotten from South America by either dolphins or vegetation debris. And that ties into our world is not static. There are so many things happening.
So there I want to acknowledge Dr. Engelthaler. That's his idea. I work with him to develop it, and it's a brilliant idea. And what he tried to explain is, why is Cryptococcus gaddii from the Pacific Northwest related to the South American isolate? The idea was that perhaps it was the opening of the Panama Canal and ships carrying water and their ballast and dumping it in the Pacific Northwest. And that then it sat there for a long time until the 1964 tsunami. The 1964 tsunami inundated a lot of these areas. And then so you can imagine that sea gaddii went from being on land to being on sea and then back on land. And that it took a few decades for selection on land before it began to cause disease in humans. It's just a tremendous idea. Again, I credit him for it, but you can begin to relate very different things in geographic changes, technological changes, things like tsunamis depositing marine organisms on land. And it shows you how all these things are connected and unpredictable.
It's also interesting if you're somebody like me who deals a lot more with bacterial diseases, the timescale is just different, and survivability, right? Bacteria, some can survive for quite a long time under the radar, etc., of course. But with fungi, it's just a whole different ballgame.
Although, we're focusing on fungi here, the same principle should apply to bacteria. And it should apply to viruses and parasites. I mean, think about it. The soil is full of organisms, and many of these organisms are adapted to soil temperatures. Many of them have pathogenic potential. We don't think about it because they don't cause disease. It's so much in us. But if you were to adapt a bacteria that currently cannot grow past, let's say, 33 degrees centigrade to 40 degrees centigrade, well, you have defeated the thermal barrier.
And vector change, dengue coming up into the United States because of warmer temperatures and it being more favorable to those mosquitoes. So you've got vector change based on climate as well.
It is like a horror show. Fungi can just kind of lie there and decades later still be there, still be waiting, and then they're a problem for us. Whereas I think that a host's relationship with bacteria, it's more immediate. Typically, you don't need to worry about this.
I mean, the thing is that most bacteria that cause disease in humans are already temperature adapted. Think about pneumococcus, staph, pseudomonas, things like that. But what we don't know worry about is the ones that we don't know because they haven't been a problem since. We have a paper that was favorably reviewed, but it's available as a preprint, in which Daniel Smith, who's a postdoc in our lab, who just in the city of Baltimore, he went into the colder neighborhoods and the warmer neighborhoods. And he has this very creative way of picking up the fungus's gooey type of candy. And what he does is he goes to the sidewalk and he pushes it in. And he picks it up, and then you take the candy and dissolve it in water and in buffer. And what he showed is that within the city of Baltimore, within maybe 4 miles or 7 kilometers, they're just talking rough distances, the species from the warmer neighborhoods are more adapted to temperature than the ones from the cooler neighborhood. And not only that, they're losing their pigment because pigment makes them get hotter. So you're having within a city evolution of this, and some of these organisms are known to cause disease in immunosuppressed patients. So this is happening all throughout the world.
Speaking of these capabilities, these powers of these fungi, the HBO show, which I have never seen, but apparently there's this big HBO show called The Last of Us. It has led to a surprising new interest by the public, in the States at any rate, in fungi. You, Arturo, wrote a book entitled What If Fungi Win? I haven't even seen the HBO show, but apparently all of the American listeners have. What did The Last of Us get right, in your opinion?
Let me tell you about The Last of Us. I had, again, not seen the show, and I began to get emails from people in the field and say, hey, Arturo, did you give them this idea? I said, I have no idea what you're talking about. Somebody wrote to me and said, you got to look at the opening clip. Anyway, so I had my 15 minutes of fame. And what happened is that many reporters and many people who were writing stories wanted to talk to me. And so the story has to do with this game involving zombies. And they become zombies because there is a fungus out there that can adapt to higher temperature and then beginning infecting people and turning them into zombies. And so what everybody wants to know is, can this happen? Is this possible? Dr. Casadevall, is this possible? And my answer was always the same. It's improbable, but not impossible. And then they say, well, what do you mean it's improbable, but not impossible? And I would say, well, there is a fungus known as a cordyceps that does this to an ant. It takes over their nervous system. It makes it climb up a tree. And the ant basically sporulates, becomes a little spore sac. So there is a precedent for a fungus taking over an animal. So once it happens, the precedent is there, even though I think it's unlikely. I don't know of any fungus that can turn people into zombies. But I do know that their fungi make neuroactive compounds. For example, LSD is made by a fungus. And people know that they can hallucinate with certain fungus. Is it conceivable that there's a fungus out there that makes a compound that turns you into a zombie? I don't think so, but I can't say no.
This is a fascinating area. And we also know that Toxoplasma, a parasite, can change behaviors in various animals that make them less afraid of predators that they normally would run away from. The cordyceps story is absolutely fascinating, and it's really exploded in Scientific America and other places. But back to science, one of the things that I recall you did was looking at the optimal temperature of humans to block you from getting ill from fungi, and that goes way back in our growth as a species.
There, I want to give the credit to Aviv Berkman, who is a colleague of Josh. When I was at Einstein, I had a whole conversation, and I said to him, you can see that for every degree between 30 and 44, you can exclude 6% of fungal species. And Aviv took that information, went back into his office, and by the end of the day, what he had done is he's taken how much protection you get by temperature and how much you have to eat to maintain a temperature. There's a well-known formula for energy expenditures to maintain temperature. He solved these two equations simultaneously, and he says, where is the maximum? Where do you get the most protection without having to eat all the time? And it turned out that it was our temperature. And that always
Our
made
body
me think,
temperature.
Yeah, body temperature, that this isn't an accident. And I have argued that proposed that the rise of mammals at the end of the Cretaceous was no accident. It always bothered me that people say, well, the dinosaurs died and then there was an open space in the biosphere and the mammals took over. It doesn't make any sense to me. We have iguanas today. We have salamanders today. How come we didn't have a second reptilian age? Mm-hmm. After all, if you're a crocodile, you can eat once a week. If you're a mammal, you have to eat 3 or 4 times a day. It's a very energy-intensive organism. By the way, that would also explain the enormous resistance of mammals to the fungi. If the mammals selected for fungi in the post cataclysmic event or that defines the KT eventually, then whatever survives is resistant to it.
But have you looked at other predictive models to integrate climate data with fungal evolutionary trajectories that could potentially anticipate the emergence of new fungal pathogens? And if so, what are some of the variables that we should be looking at?
So I have worked on this intermittently, because this is not the kind of stuff that's supported by grants or anything. But prior to COVID, I was working with some collaborators in Europe, trying to come up with an algorithm to predict. For example, if you have two fungal species, and one has a maximum of 25 degrees centigrade, and the other one has a maximum of 35 degrees centigrade, I think you'll worry more about the one that is 35. So if you were going to make a threat matrix, what would you worry about? Well, you would worry about fungi that currently cannot grow at 37. But that can cause disease in animals, can cause disease in plants, because that means that they have the capacity to evade at least those immune systems. So I think it is possible to do that. I think what is needed is time and some degree of effort and trying to link complex databases. The other thing is that you can do this relatively easy in the lab. So how do you do it in the lab? Well, you take your favorite fungus and just put it in the incubator and slowly increase the temperature. And it's remarkable. They have remarkable adaptability to do that. It doesn't mean that they like living in a warmer world, but they can certainly live in a warmer world.
I mean, obviously, everyone adapts, not just fungi. Are human immune systems adapting in step?
That's a great question, Angela. And I actually been looking into that. There has been very little studies done in this area. But what is available is that once you take a human and you begin to put them in really hotter temperatures, like, for example, we're having a heat wave here in the East Coast right now, it puts tremendous stress. And the stress includes in the immune system. So we may find that in a warmer world, we are facing organisms that we didn't face before with immune systems that are degraded as a result of the stress. I don't think it's going to be immunosuppression like we see with HIV or corticosteroids, but it is very clear that stress degrades immune systems, and that will be a whole new factor.
Oh, no, Arturo, this is depressing. My question was more hopeful. I was thinking our immune systems are going to get stronger because we also want to survive, right? We're also in this game. But you're saying, no, it could get even worse for us. Our immune systems may adapt the wrong way.
Yeah, and Angela, that brings up, there was a study a few years ago, a fascinating study, in which they looked at temperature, human temperatures over 100 years. We are cooler today than our great-grandparents. Why is that? Because those who lived at the beginning of the 20th century, for example, it was a dirtier world, and a world where there was more inflammation. More likely that you were carrying indolent tuberculosis, you were carrying parasites. And that inflammation was enough to drive temperature by 1 degree. So the fungi are adapting to higher temperatures, and we are getting cooler and probably going to get stressed by heat waves. So I think the future is going to see a collision between these types of organisms, and it's not going to be good for us.
And not just that, people worked more not sitting down like we are. And so just doing physical work or going for a jog more often changes your temperature. And if we are more couch potatoes, we will be better incubators.
So here is a thought that just popped on. So at the beginning of the 20th century, temperature was used as an antimicrobial therapy. In fact, the Nobel Prize in 1926 was given for using malaria, giving people malaria to treat syphilis and gonorrhea. But by the 30s, they could raise your temperature in some machine, and you could take a person, put them in, and you could take them to 105 in half an hour without any problems. One thought is that we have abandoned temperature in medicine. And as we're dealing with more and more resistant organisms, to me, that is an area that could be brought back. I'm not talking about infecting people with malaria, but we know how to induce fevers in ways, for example, with cytokines and things like that. And when you're dealing with some of these organisms, they get into trouble at higher temperatures, for which our drugs don't work very well. Thinking about hyperthermia, therapeutic hyperthermia, and bringing that back could give us brand new tools.
And a great example of that, Arturo, is with fungi, because localized sporothrix in a pregnant woman the treatment of choice is local increasing temperature.
Exactly.
So from that itself is a perfect example.
So Josh is talking about sporotrichosis. That's the fungus that people get sometimes. The classic thing is a thorn bush and you get it. And it prefers the arms and the legs. And if you can wrap them up in heat, you could treat the organism without exposing the rest of the body to drugs.
This is so interesting. On the bacterial side, I have also really wondered about this because obviously fever is there to protect us, right? We make fever in response. It's a defense. And yet, like you say, now we so easily give paracetamol, acetaminophen. We put down fevers all the time. And yet it's probably not such a good idea. The problem is we're clinicians, right? And we do these big trials and we get one shot at these trials, right? There was an Australian study done, and I think this must be now 10 years ago or so. It was a fairly big trial, in theory, quite well powered. It was done by intensivists who withheld paracetamol from patients who were in septic shock at times. And I think the problem, and again, whoever's listening, I'm sorry if I'm misquoting this study. I don't have it on hand. But from my memory, they were pretty agnostic as to whom they withdrew the paracetamol from. So even if you had super high temperatures, they weren't giving any paracetamol. So it was just a withdrawal. And those who had really, really high fevers, they were sort of entering dysregulation anyway. They did poorly. And so the conclusion of the study was it's dangerous not to give paracetamol. There were more events in the no paracetamol arm. And now, unfortunately, we're kind of stuck with these results, right?
I looked into the fever. The fever literature is enormous. And you can find that fever does good, does bad, et cetera, et cetera. But here's something for you to think about. If you, Angela, go hiking in the Swiss mountains near you and you fall and you get a gash in your leg and it's contaminated with soil organisms, 2 degrees of temperature is going to give you an enormous protection. But if you now get an infection in the hospital, for example, Pseudomonas, Acinetobacter, all those organisms are temperature adapted already. So it's very hard to demonstrate the benefit of fever. What I would argue is that just like we take organisms from patients and we do antimicrobial susceptibility, it may be possible rapidly to get temperature susceptibility. And if you have that information and you have an organism that crashes at 38 degrees, well, that's how you want to do the clinical trial. I think the problem has been that these issues haven't been taken care of. I don't think fever is going to help you that much with a bacteria that can grow at 42 degrees. But it could be enormously life-saving for some organism that becomes borderline viable at 38, 39 degrees.
Yeah. So in that ICU, you're not seeing the organisms that are
you're not seeing them, right? Except there may be the fungi. Some of these unusual organisms that affect or immunocompromised patients, they may not do very well. I mean, the Aspergillus are in a class of their own. They can grow very well at higher temperatures. But a lot of these strange fungi that we have to deal with sometimes in immunocompromised patients, that may be a population to look at.
Mm-hmm.
So along that line, Arturo, in the healthcare setting, we know that dual infections are not necessarily uncommon. And the ability of a bacteria and a fungus to cause disease concurrently or even synergistically is there. And what are your thoughts on that cross-kingdom lethality or synergism or additive effect that's happening, whether it's biofilm or whether it's distracting the immune system in some ways? After COVID, we saw Mucor and we saw Candida auris and we saw Candida albicans. And after influenza, you see Staph aureus and pneumococcus.
I mean, I think what you're describing, an organism that damages the host and then makes them susceptible to the next one. But you also have the phenomenon that we often tend to think of infectious as a monoculture, because what we have is what we can recover, but there may be other things that you don't see. I think the big progress there may come as we introduce more and more sequencing into medical practice. That is, sequence what's there, and then you may see multiple organisms. And it may be some of these times in which we use antibiotics and we can't help people, is that there's something else in it.
Can you comment on the damage response framework that you and Lizan Perovsky introduced in terms of understanding host responses and pathogenicity through that dual lens of host and pathogen?
So this was a good 25 years ago. Lucian and I used to teach a course. After teaching the course, we didn't want to do what people call the bug parade. In microbiology, they do the bacteria, they do the viruses, and we wanted to have some ideas to tie things together. And from the class notes, it was apparent that people get into trouble when they have a weak response to a microbe or an inordinately strong response to it. That is, that damage and death can come at either end of what is a parabola. Imagine a parabola, and imagine that health is somewhere in the middle. So that began to explain a lot of organisms and a lot of diseases, because let's just take a fungus, let's just take Aspergillus. So Aspergillus, in a setting of weak immunity, having no neutrophils, kills you in the left part of the parabola. Now take a farmer who has been exposed to mold and has been exposed to, they develop hypersensitivity pneumonitis. Well, they can also die, but in this case, they're dying from an overexuberant immune response. But this carries to bacteria too. At the infectious disease conference this morning here at Hopkins, we were talking about pneumococcal pneumonia. If you have pneumococcal pneumonia, what kills you is inflammation. It's not the organism. The organism is not making toxin. It's not killing you by toxin. And now there is evidence that, in fact, there is increasing amounts of evidence that you can decrease mortality by using corticosteroids. And if you think about COVID, and now we know that very early in COVID, if you increase immunity by that alpha interferon and beta interferon, it can make a benefit. But then if the immune response essentially overshoots, what gets you into the hospital is inflammation. And then those people are treated with IL-6 inhibitors, and they are treated with steroids. And it's a comprehensive way to look at disease. And what we're missing today in the early part of the 21st century, and I hope maybe some listener can think of developing, is a mechanism by which a physician can go to the bedside and can know this patient is really sick. Is it really sick from the organism because it doesn't have sufficiently strong immune response? Or is it really sick because their immune response is overexuberant? Because we have the drugs for either way, but we don't know how to use them because we cannot place the patient into where they are in the process.
Yeah, unfortunately, the key point, there's so much inter-patient
variation.
Yeah, and this is our problem with our trial designs, right?
That we treat everybody the same. And then they tell you can't do subgroup analysis.
Right. And you probably don't have the money because you'd need a lot of patients to have the power to do those subgroup analyses. Yeah.
I understand very well that you can sit there and you can look at the subgroup analysis and you can convince you of anything. But on the other hand, I also think that one should be able to do it and realize that, and that is the case, because that generates the hypotheses for the next trial.
And you would hope that you could maybe identify a biomarker, some kind of marker of where's the tipping point for this patient, where is it too much inflammation, rather than having to throw everyone into the same trial and hope that you show something with a whole bunch of human beings who are very, very different in the end.
You know, in the area of cryptococcus is a remarkable disease in which we now are in a situation in which the HIV-related cryptococcus has a better prognosis than the non-HIV-related cryptococcus. And clearly what is happening is the other ones have died of inflammation in the brain. So you also know that there is evidence that you can add gamma interferon to the HIV patients and they can do better. You can move them to the right on the parabola. And then the patients at the other end have so much inflammation, you need to move them to the left. But what we really need is we need to have something by which a physician can order a test and know where that patient is in the inflammatory spectrum. Do I treat him with a pro-inflammatory? Do I treat it with an anti-inflammatory? And I think we're going to see that. I think that's going to happen in this century. And it's going to be a huge advance because we all treat patients that antibiotics, even often, you can't save the patient.
I want to add another layer to this, Arturo, and bring up your environmental boot camp discussions in terms of why are some of these environmental organisms such lethal pathogens in us? What's happening in the environment that has trained them or given them the wherewithal to cause disease in us?
I think it's important to recognize things that bother you in science and medicine and then to do something about it. So I already told you that what bothered me was, how could the mammals have taken over? All right, we covered that. But the other thing that bothers me is, what is an organism that lives in pigeon excreta have the capacity, when you take it out of there, to give it to a mouse or to a human and to cause such severe disease? I mean, why? Why kill a host when you have no need for that host on it? So the idea began that there has to be something out there that was selecting for traits that would allow it to cause disease. Josh was there when Judy Steinbergen in the lab began looking at amoeba. And it turns out that the cryptococcal interaction with amoeba is very similar to that of a macrophage. So as far as Cryptococcus is concerned, well, when I'm in the pigeon excreta, I have to deal with amoeba. When I'm in somebody's lung, I have to deal with macrophages. And in bacteria, you have the similar present, although it's different, with Legionella. And many of these soil organisms have now been shown to pretty much deal with thousands of species of amoeba. So when they run into a macrophage, well, they deal with it the same way.
So it's a dead end for that particular fungal colony. But hey, overall, it's advantageous to still be dealing with amoeba.
If they kill the host, they can go back into the environment.
That's true.
Right.
That is true. They're not entirely dependent on their host. Yeah.
If you kill a human, they'll bury you. or they'll incinerate you. But if you kill an animal, the animal rots, it goes right back into the environment. So it's acquired new traits, and it may make them even more or better or worse or dealing with amoeba. But these cycles just go on. So the idea is accidental virulence.
Arturo, I have a different question for your book, Will the Fungi Win? I would say it's like, why haven't the fungi already won?
So that raises something else that bothered me when I give these seminars. People say, why? Why didn't the fungus adapt? Why didn't the fungus adapt to higher temperatures? And that led me to ask the following question. Is virulence a good thing for a microbe? And together with Lizanne Perosky, we wrote an essay a few years ago, which was called The Cost and Benefits of Virulence. And I would argue that an organism that chooses an association with a host is taking a big risk. The host may go extinct. Also, you may become so dependent on the host that you can't live in the environment. Take an example of that, Mycobacterium leprae. You can't even culture it if you give them a really good agar. You have to procreate it in armadillos. So it is very dangerous for a microbe to associate themselves with host. So when people say, well, why haven't the fungi adapted to be 37 so that they could eat humans? I say, because that may not be a good idea. To think at it from that point of view. People think about superbugs. That may not be good for a superbug to be totally loaded up with antimicrobial resistance and things like that. Because if we pass from the scene, where is that organism going?
So that gets us even to space. And Arturo, you've done some really cool stuff with the space station and fungal melanin. And there's a lot written right now about organisms on our space station or the Chinese space station. What's going on in space?
Fungi are doing very well in space. In fact, the fungi will survive the exposed to space. If you go and you put down International Space Station, fungus images, you will see that they're growing indoors, demolishing the electronics. They're a major problem. So I want to, again, acknowledge other people because everything that I've done in my career has been done in collaboration with terrific scientists. So Radamés Cordero established his collaboration with NASA, and we just had a paper published on using fungal melanin to protect materials in space. But there was another earlier collaboration with Ekaterina Darachova, in which we were again interested in something that was in the news. The fungi were growing in the Chernobyl damaged reactor. And there, it turns out that we provided evidence that they were using radiation for food, that just like plants use visible light to grow, that the fungi have the capacity to harness radiation. So fungi can be adapted to grow in soils of Mars. And I think that fungi are going to be essential for us to become a multi-planet civilization. We're going to need them to help terraform planets. We're going to need them to protect us from radiation. We're going to need them for food. We're going to need them for a lot of this thing. So what if fungi win? I would say they already won. And if they win, they're also good for humanity.
We have to harness them.
Right. We have to figure out how to use this enormous biological power.
Can you tell us about the humongous fungus?
Okay, so there is a fungus that lives here in North America. It lives in the Northwest. And the way you can tell, it's under your feet, so you don't see it, except when the mushrooms come out. But you can mark where it's been because the dead tree is above it. And this fungus is thought to weigh 35,000 tons, which is larger than a World War II battleship. It is thought to be several kilometers in area, and it's under your feet. That's the largest one that we know of, but there aren't people out there doing this kind of work. And how do you know it's one organism? Because if you pull up the mushrooms and you take them to a lab and you do a sequence, you can find that it's the same organism.
It's important for us to understand the scale.
The scale is just enormous. And the important thing is the fungal world is the unseen world. You don't see them. They're either microscopic, you can't make them out with your eyes, or they are below ground. And they come out when it rains. They come out to digest matter, a dead tree in a forest. So we could argue that the largest kingdom is also the most cryptic, the one that we know the least.
And they communicate. I mean, they can even sing. There are some really cool videos on that. But how about sharing some other science that you've done, Arturo, in refrigeration?
This was one of those fun Friday afternoon ideas. So Radamés Cordero found that these fungi were colder because during COVID, we had a thermal camera that we used for studying melanin, and he began to go for walks and taking pictures. And when he took these pictures, the mushrooms in the forest are always blue. Why are they blue? Because they're colder. And it turns out that had been described, but his major contribution is to extend the principle of hypothermia to the microscopic fungi. So it turns out that when Candida, Cryptococcus, things like this, grow in a plate, they're colder than their surroundings because they basically transsudate constantly. And this transsudation keeps them colder. So musing on a Friday afternoon, I said to Radamés, I said, hey, we can make an air conditioner out of this. So he went to the store and he bought himself a few kilos of mushrooms and he put them in a styrofoam container, laboratory containers. He put a hole on it. He put a fan from a computer and he dropped the temperature by 10 degrees centigrade. As long as the fungus has their moisture, it's transudating and cooling itself. The same principle why you're cold when you come out of a shower. And the beauty is that as long as it's of water, it cools it off. And then when it no longer cools off, you can take the mushrooms, throw them in a pan and cook them and eat them. So I will tell you that we apply for a patent on this. And my life with patents have been, you send patents in and patents come back. This is the only patent that didn't need to be revised. I think the patent examiner looked at this and said, this is really different. A fungal air conditioner. And if you're interested in this story, and it is published in PNAS a couple of years ago.
Great pictures in that publication, too.
Right. So we made a fungal air conditioner, and you can feed it with mushrooms from the store and take it with you, and it could cool off your beer, then drink it off. And when it stops working, just cook the mushrooms and eat them.
So a big point to the humans there.
That's
I think,
right.
In some respects, we are winning too, right?
Right. We're learning how to use them.
Yeah. So unfortunately, getting back to some more serious stuff for the clinicians among us, with certain fungi, like, for example, histoplasma, coccidioides, that we know are expanding their range because of global warming, how should clinicians and epidemiologists recalibrate their diagnostic frameworks, their surveillance frameworks? I know in your book you do talk about the fact that a lot of physicians were not asking the question, we're not suspecting fungi up front. And do we need to change that?
I think, to put it simply, the fungi are changing their geographic locations faster than medical education. For example, here in the United States, you learn that histoplasma is the Ohio River Valley. Well, we have histo in Baltimore. It used to tell, well, coccidioidomycosis there is out in the Southwest. Well, now coccidioidomycosis is turning up in a lot of other regions. So I think that physicians need to, at least when it comes to this kind of organisms, realize that what you learn in medical school, what you find in the textbooks, has been made obsolete by the fact that climate is changing very rapidly and humans are moving things around. So the index of suspicion has to be higher than it was maybe a couple of decades ago.
We talked just before a little bit about Cryptococcus neoformans, how it was clearly associated with HIV in the past and clear immunosuppression. We just actually had a case of Cryptococcus neoformans in a perfectly immunocompetent man. And it's still, in my own mind, it doesn't fit.
Now we know why some of those people get it. And this is work that was done at the NIH. So it turns out that occasionally, randomly, bad luck on it, you begin to make an autoantibody that knocks out a cytokine. So they become essentially knockouts for a cytokine. GM-CSF is a common association. Because again, we always had these patients who seem to have normal immunity that show up with Cryptococcus. In your case, it's a perfect one. That clearly that individual was exposed to Cryptococcus for the first 40 years of their lives, and they didn't get sick. Then something happened by which they're now. But the fascinating thing is that the immunosuppression may be very narrow and very specific. So if you guys are still caring for that individual, it may be worthwhile to try to contact one of the laboratories that is looking at this and see if that individual has made an autoantibody to one of the major cytokines. So their immunity is still good for a lot of things, right? They can still go through life and all that. But for this individual pathogen, they are now highly susceptible.
Okay, autoantibody.
It's tying on autoimmunity with immunodeficiency.
Yeah.
It's a whole new frontier that we need to think about.
But on a simpler level, sometimes it is the strain and sometimes it's the inoculum. So if you get enough of something,
it doesn't matter. If you get enough of it, you can overwhelm the immune system.
And great examples with that are histoplasma. When people go out to cut their Christmas tree and the guy who cut the tree gets sickened in the ICU and the person who's standing 5 meters away gets a little cough. The challenge of these is that there are so many facets to why somebody gets ill that to create a single paradigm is not going to work.
One of these things that needs to be done, and it is not being done because it's not considered cutting-edge research, is we need to map the natural world. We don't know what's out there. This is not high-tech research. Different parts of your backyard here are very different. And we need to do this because the environment is both a source of new bugs that could help us, as well as major threats. And the only way to know what's out there is to go out there with the tools we have and to begin really studying the environment. So if you had unlimited resources, I think that would be one of the best use of the money, even though it's not the kind of research that people say, well, that's what I want to do. No, you got to know what's out there. Just like there was one time in which we didn't know the shape of the continents. And you had to map them, right? I will tell you further. And once you knew the shape of the continents, you know that certain continents fit together. And eventually you got plate tectonics and you had a coherent view of geology on the planet Earth. So if you mapped the natural world, you may get insights for infectious diseases, for beneficial microbes, for the cycles of the Earth that could be comparable to the discovery that the continents move.
Yeah, and you'd also find a whole lot of antibiotics and antifungals in the process, right? Yeah.
And maybe even phage. We haven't found phage to fungi.
In the category of, right? Yeah. So, there are no phages to fungi.
Well, there are viruses to fungi. Generally, they are not called phage because the fungi are eukaryotes. They're, in fact, the animal's closest relatives. The fascinating thing is they do exist, but thus far, no one has found one that goes from the outside. Just like with bacteria, you can put in phage and you can see plaques. You don't have that with the fungal world. And I don't know whether that's a limitation of how much work has been done, or I don't know what's the real biological difference.
So in other words, we do need to map better.
We need a lot, exactly.
Yeah. However, that is one of those projects that's very long-term, big investment for very distant gains, and we are not in a world right now.
We are not good at this,
Yeah.
So Arturo, we really have the most deep appreciation for you taking the time to speak with us. You've shared complex and simple thoughts on many different topics. You've also given us some scares to consider as we move forward. It's been an incredibly helpful and illuminating discussion, and we want to give you the opportunity to share any last-minute messages with the listeners.
What I would say is that what you do is really important. Trying to get science to the public has never been more important. And I commend you for it. And actually, it's been a wonderful hour chatting with you. And if we can think of something else to talk about, I'm happy to come back.
Thank you very much to my two fungi. Thank you, Arturo Casadevall at Johns Hopkins University in Maryland, USA. And thank you, Josh, for being my excellent co-host. And thank you for listening to Communicable, the CMI Comms podcast. This episode was hosted by Josh Nosanchuk in New York, USA, and Angela Huttner here in Geneva, Switzerland, editors at CMI Comms ESCMID's Open Access Journal. It was edited and produced by Dr. Katie Hostetler-Oy and peer-reviewed by Dr. Robina Ertz from University Hospital Antwerp, Belgium. Theme music was composed and conducted by Joseph McDade. This episode will be citable with a written summary referenced by a DOI in the next 8 weeks, and any literature we've discussed today can be found in the show notes. You can subscribe to Communicable wherever you get your podcasts, or you can find it on ESCMID's website for the CMI Comms Journal. Thank you for listening and helping CMI Comms and ESCMID move the conversation in ID and clinical microbiology further along. And by the way, I always say fungi. In the States now, do you say fungi?
There is no wrong way of saying it. You can say it fungi, 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 even fungi.
And Arturo is a fungi.
Yes, and you guys are my fungis. Yes.